And ladies and gentlemen, welcome to this conversation we're about to have today on how we can use FMEA, or sometimes called functional block diagrams, to better understand your item. And I'm going to be honest, but a sneaky ulterior motive, or ulterior message, I should say, guiding today's conversation. And to start off today's conversation, I'm going to go back to a case study, or not even a case study, just a story about what actually happened in a very bad way back in the day. So some of you might recall, I routinely use, not routinely, every now and then I use the example of this Xylon bullet-resistant vest, which was manufactured by a company called Second Chance Body Armor. And the vest was made out of Xylon fibers provided by a company called Toyobo. And the reason why this was at least initially, very successful vest is because Xylon is a very, very powerful fiber in terms of its properties, not least of which is its strength. However, in 2003, something bad happened. That was a 40 caliber round penetrating a vest. Problem with this is that it absolutely should not have. Now, we used to call these bulletproof vests. We now call them bullet resistant vests because you can never say absolute certainty whether a round can penetrate a vest or not. For example, being struck by a round fired by an assault rifle 6 inches away is a whole lot different to being struck by a round from an assault rifle that's shot 400, 500 yards away. And so, notwithstanding, the reality is that a 40 caliber round, which is fired from a short barreled weapon, just simply should not have penetrated a vest, but it actually did. And in the ensuing investigation, it turned out that they pulled some of the Xylon fibers from this vest, and they found they were 30% weaker than brand new fibers. And that was a problem for obvious reasons. And they then said, this is actually troubling. So what they started doing was investigating all the other Xylon-based vests that were being used by law enforcement agencies across North America. When they started testing this sample of vests, they took the vests and didn't necessarily just do scientific testing. They actually put these vests on dummies and fired rounds at them, which is the way the National Institute of Justice in the US mandates testing to be able to for you to be able to say that, yes, this vest is resistant against these caliber rounds, etc., etc., etc. But of those vests, 58% were penetrated by rounds they were supposed to defeat, which is very, very bad. 38% had excessive backface deformation, which means the round didn't get through, but the person wearing that vest was still going to have a very bad day because essentially there was a lot of movement in the vest against the skin of that person, which had the potential to cause substantial injury. Only 4% were okay. So let that sink in. And these vests, which were supposed to defeat the rounds that were being fired at them, only 1 in 25 of the vests that had been worn or used by law enforcement agencies across North America were actually still able to do what they were supposed to be able to do. So what was going on? The reality is that when we are looking at something like a bullet-resistant vest, we need to understand how it's supposed to work. Now, if you can see here, you can see I've got a cross-section in a way of the fiber weave that is used to create bullet-resistant vests. Now you can see on the right-hand side, I've circled a bullet, a round, an incoming round, the round that's being fired at this fiber weave. Now, we often, depending on who's got any sort of military or law enforcement experience, there's two sort of broad categories of bullet-resistant vests. The first category is whether the vest is based on a fiber ceramic composite, and the ceramic is an extraordinarily strong, tough material. It's not flexible in any way, shape, or form. But the reason why you have those ceramic vests is because the first thing your bullet-resistant vest to do is to essentially mushroom the round coming in. You might have heard in movies and things like that, you have these things called armor-piercing rounds. And all those rounds are designed to not mushroom when they hit the surface of the thing, the armor they're supposed to get through. And the reason why we want that mushrooming is because then you have the energy, the kinetic energy of that round being dissipated across a larger area. And so the more mushrooming you get, the much easier it is for that vest to stop that round from getting through, which is why ceramic is so useful, so beneficial. But ceramic is not flexible. And so in practice, you are limited to have, when you use ceramics, to simply having maybe one plate at the front and one plate at the back of the person wearing the vest. So these ceramic plates are put in pockets. And as someone who's used these vests and these plates in the past, it doesn't protect a whole lot of the upper torso. It maybe it's a square foot area. And so that, while ceramics are wonderful in that terms, they do a great job of mushrooming that initial round, they are very limiting in that they are not flexible, and so therefore can only fit on a small part of the person wearing said vest. So when you have just fiber weaves, no ceramics, the benefit is that you are able to have that vest be flexible, so you can wrap it around the upper body of the person wearing it. It is also breathable. You can have moisture from the sweat passing through the fiber weaves. And as you can imagine, when you're wearing these bullet-resistant vests, these flexible bullet-resistant vests, they're one of the world's heaviest, warmest blankets as well. And so a lot of sweat will be created, and so you do want to have sweat passing through, and fiber weaves do allow you to do that. But the flip side is that fibers are very flexible. They're not very good at making sure that initial round mushrooms the way you can see in the screen right now. So it's always a compromise, but there will be at least some initial mushrooming on impact. And when that round does mushroom, the next thing that happens is that it creates what's called a shear plug, where the top couple of layers of that fiber weave essentially detach and create this sort of cylinder, this plug, in the same shape as the area of that now mushroomed round. And that's actually very, very useful. The reason why is because when you create that shear plug, if those fibers detaching or fracturing, each one of those fractures absorbs energy. So this is exactly what the bullet-resistant vest is supposed to do. You dissipate energy by shearing and local fracture. And of course, once a vest has defeated a round, it needs to be replaced. You can't ever use it again because the area where the vest was shot is now damaged, but ultimately successful, hopefully, in preventing the round from getting through. And so after we created this shear plug, the next thing that happens is a conoid shock wave is generated and reflected. All right, so that conoid shock wave gets generated and reflected through the fiber weave. And that shock wave then causes delamination, more fiber yield and fracture, which is always good, because every time you have fiber that fractures, it absorbs more energy. Every time it delaminates, it absorbs more energy. And the stronger the fiber, the more energy it is absorbed when it fractures. And so we want really strong fiber, like really strong fiber, which is where Xylon came into play. So when it comes to fiber, we can look and compare different fibers in terms of their physical properties. So for example, this chart here has a bunch of different fibers plotted on this chart. The horizontal axis is what's called the specific modulus, the elastic modulus per mass density, often called the stiffness to weight ratio. And so this is essentially per kilogram mass, in a way, the amount of energy that would take to stretch these fibers by a unit distance. And you can see that some fibers absorb way more energy when they undergo elastic deformation. You can see in the bottom left-hand corner, steel. So we're talking about fibers which are incredibly strong, incredibly strong. And some of these fibers, including what's called ultra high molecular weight polyethylene, like the Spectra 900s, their specific modulus actually increases the faster it is deformed. So in a way, the faster the bullet, if you have a vest made out of Spectra 900, the faster the bullet, the more energy is absorbed by the fibers. It's a very useful property. And on the vertical axis, we have what's called the specific strength, which is another, some people call this the strength per mass density or strength to weight ratio. So the horizontal axis is all about how much energy is absorbed when it stretches. The vertical axis is all about how much energy is absorbed when it fractures, when it breaks. And it's in the top right-hand corner, we have this single data point of PBO fibers, and PBO stands for polyphenylene benzobisoxazole, and the registered trademark name for this fiber is called Xylon. So let's look at polyphenylene benzobisoxazole fibers in greater details. And this will be the last time I say polyphenylene benzobisoxazole fiber, because I'm going to use the acronym PBO moving forward. Now, the fiber itself is made up of lots of polymer molecules stretched along that direction. Now, a polymer contains very large molecules linked together in chains of repeating subunits. But it's a little bit more complex than that in a good way, because these fibers, which are very small, you can see them. So they're sort of on the boundary between what is visible to the naked eye and what is microscopic. But if you were to zoom in and do a cross-section of these fibers, you would see that when they spin these fibers, they essentially create an abseiling rope, where you have a surface or a sheath on the outside of the fiber, which is very, very thin. And most importantly, you have these microfibrils, these little fibers, little ropes on the inside. The reason why this is really useful is because whenever you have one of these microfibrils fracture, that fracture doesn't then extend to all the microfibrils next to it. So yes, these things will degrade over time because they will fracture just from bending this and bending that. But when you have these lots of microfibrils, it sort of contains those little mini fractures to not go through the entire fiber diameter. Now, Xylon, unfortunately, undergoes what we call aggressive hydrolysis. NASA identified this in the mid-90s. And hydrolysis is a chemical reaction where water molecules break chemical bonds. And so if we zoom in to an incredible resolution and we look at the molecules themselves, this is the polymer molecule. You can see we have these repeating units. Every atom you see with a C for carbon, N for nitrogen, O for oxygen, H for hydrogen. All those colored atoms, one mer unit. Now, within this unit, there's this oxazole link, which is a ring made up of 3 carbon atoms, 1 nitrogen atom, and 1 oxygen atom. And what happens when water comes along is that you get H2O molecules. The first thing that happens is that at the bottom, one of the H2O molecules interacts with the oxygen and carbon atom to open up the link. So we're starting to lose a little bit of strength. And finally, another molecule will come along to finish the job. Now, the reason why polymers are very, very strong is because the covalent bonds, the bonds between adjacent atoms, are as strong as they come, one of the strongest forces in nature, but they act over a very, very short distance. Gravity is very weak, but acts over a very long distance, for example. And so we want to maximize the strength of these covalent bonds between these adjacent atoms, and those covalent bonds are represented by those black lines. And that's where things like Kevlar, ultra high molecular weight polyethylene, polymers like that, that's where they get their incredible strength from. They have these molecules which have millions upon millions of atoms in them and these repeating units. So essentially the fiber, to the fullest extent possible, is one long chain of covalent bonds between atoms. So they're very, very strong. But unfortunately, it doesn't mean they're immune to let's just say, bad things happening. So because we knew from previous previous discussions that hydrolysis had been discovered as a possible, well, as something that does destroy Xylon. Spidey senses were tingled from the very start. So hydrolysis was suspected. And then this thing called failure analysis was conducted on Xylon fibers. Now, why is that important? Because we need to understand how this thing failed. And to do that, the National Institute of Justice in the US conducted some experiments. They got some brand new Xylon fibers and they started testing them. They got some brand new Xylon fibers, and you can see on this chart here, we have on the horizontal axis residual exposure time in days. So up to 500 days on the horizontal axis, so 1.5 years. On the vertical axis, you have residual strength. 100% represents the advertised strength of Xylon. And so if you were to put a bunch of fibers in an environmental chamber and then take them out in series successively and then measure their tensile strength, you could create a chart like this, where you have these red data points indicating how strong those fibers were when they were removed from, in this case, a chamber, which was held at 55 degrees Celsius with 0% relative humidity. So not a molecule of water to be found in the chamber where these fibers were kept in a very heated state. You can see that while there is perhaps some decline in tensile strength, it's not super obvious. But at the same time, they're conducting other tests where fibers were stored in still warm environmental conditions, but with 60% relative humidity. You can see that as they were taking fibers out over the first 4 months or so, the residual tensile strength for each fiber they took out was getting smaller and smaller and smaller. And so for these fibers that were left, they said, you know what, let's just see what happens when we reduce humidity and see how quickly things degrade. And yes, tensile strength was still degrading, but at a lower rate. And when they took it down to 5% relative humidity, so not much water at all, at much lower temperature, yes, the tensile strength was still going down, but at a much lower rate. And so as a result of failure analysis, they concluded that hydrolysis was confirmed as a failure mechanism that leads to the rounds penetrating the vest. Now, question for you guys. What's the difference between failure analysis and root cause analysis? Does anyone know? If you got an answer, please feel free to share it in the chat window. Anyone who's brave enough to venture an opinion. Less detailed, yes and no. So failure analysis is check how it fails, love it. And how's that different to root cause analysis? Root causes is why. That's as good an answer, as succinct an answer as you could possibly hope for. Yes, Kevin points out failure analysis goals determine the physics of failure, which is what Giovanni's referring to when he says how it failed. The next question is to understand why this happened. Beautiful. So I think we're on the same page. RCA could involve failure analysis inside the methodology. Every single one of those responses is 100% correct. So failure analysis in this case can identify that hydrolysis was the failure mechanism involved. Now, in this tale of woe, what actually happened was Toyobo was the manufacturer behind the Xylon fibers, advertised these Xylon fibers to, yes, be susceptible to hydrolysis, but at a slow rate, because every fiber will degrade over time. So there's no such thing as a fiber which never degrades. For example, a lot of Kevlar, which is chemically similar to Xylon, will degrade when exposed to ultraviolet light, which is everywhere. So you can coat Kevlar, you can protect it, but ultraviolet light will get through. So Kevlar will eventually degrade over time. So it's not about whether it degrades or not, it's about how quickly it degrades. Then Toyobo didn't really study the phenomenon too much. They were rushing to sell an amazing new fiber. Second Chance Body Armor jumped at that opportunity, and they themselves didn't validate or verify the claims made by Toyobo regarding how quickly these things degraded over time. And then one employee within Second Chance Body Armor was sent a memo by Toyobo saying that there were concerns that Toyobo had underestimated the rate at which these things degraded due to hydrolysis. And so the employee at Second Chance Body Armor then initiated, in this case it was a he initiated his own tests and confirmed that the xylon fibers they were receiving were degrading way faster than what was acceptable. And so he raised his concerns, and then what came next was truly shocking, because Toyobo and Second Chance Body Armor, the leaders of these organizations, got together and agreed to bury the results. True story. And the guy who conducted the test was essentially came out eventually as a whistleblower. Eventually, he was awarded a $20 million settlement after 18 years of pursuing his rightful claims as a whistleblower. But the reason why I'm telling this story is because many people think that hydrolysis in this scenario is the root cause of failure. Is it? Or is it the people who pretended, hoped it didn't exist? And I think you all know the answer to that. So failure analysis is great at identifying, for example, that hydrolysis was the failure mechanism at play for why these vests failed. But the root cause of failure is the people who pretended / hoped it didn't exist. And so in this conversation, we're going to talk about failures a lot because, well, it's a Shendo. Shendo is all about reliability. Reliability is a probability that failure will not happen. So failures are front and center of our thinking, and they're events where an item inherently ceases to perform a specified or required function. And so to find out what our item is supposed to do, to understand what our failures are for an item, we need to understand what our item is supposed to do and what our item actually is. Now, when I'm involved with, for example, FMEAs, there is a tendency with the people I'm working with, especially when I conduct training, to question why I spend so much time on understanding the requirements and the functions of the thing we're supposed to do. I spend so much time trying to come up with use cases, describe how our thing's going to be used. And as a rule, that questioning is pretty heavy at the start of the FMEA training or the FMEA I'm facilitating. But by the end, as a rule, people say, thank God we did that. And we're hopefully about to find out why. We're going to focus on my smart lock, the example I use a lot in many of my webinars and courses. The smart lock is a wonderful device, but we need, before we start designing this, whatever this is, we need to have a really good idea of what it is. And the number of organizations which genuinely believe they understand what their thing is, but when it comes to drilling down in the details, they don't. It's astounding. And one of the reasons why is because when you look at a smart lock, or when you look at an angle grinder or a car or a rocket, everyone thinks of the central pieces of that device, that thing. It might be the engine and the transmission and the wheels of the car and the drivetrain. That's what most people think when they first think about designing reliable cars. You think about rockets, it's the fuel, it's the actual cones and everything else that is associated with essentially the core functionality. But a lot of failures are caused by not being on top of everything else. And even before we start designing something like a smart lock, we know that in this case, we're going to have 17 components, 16 of them will be different. And we know that what the configuration will be roughly similar to this. Now, some people will say, hang on, we might change this configuration during the design. We realize something's not feasible and everything. And we do testing and realize this is too hot, or that's too cold, or this is too brittle, or what have you. And go, that's 100% fine. But you're going to be fine tuning this configuration as opposed to rebuilding it from the ground up. And so I often find that people use a lot of engineers or designers say, well, we don't know exactly what it will be, so let's pretend we don't know anything about how it should be. And that means that that's essentially a get out of jail free card when it comes to actually thinking about how these, for example, components can interact to make sure it works, because a system is nothing if those components don't interact. One of the best ways to understand how these components interact, make sure it works, is to start by organizing our thoughts. Now, this is where the concept of hierarchy becomes very important. So in this in this discussion, I'm going to use numbers to represent hierarchy, and 1.0 represents the system level item. And so in this case, 1.0 represents the smart lock itself. Now, within the system, we've got a bunch of components and subsystems. So when we drop down, we can see that we have subsystem items. You can call them components, you can call them parts, whatever word works for your organization. And within these subsystem items, you might even have more parts or elements or components. Maybe we call these components. So look at the motor, for example, we have components or parts. In this case, 14 different components or parts that make up an electric motor. And before we do any level of design for a smart lock, we know that there's going to be an electric motor. We know that the electric motor will have, we expect, these 14 components or parts. There's no reason why we have to wait until we design, purchase our first electric motor from the supplier before we start thinking about how the brushes are going to interact with the other elements of this subsystem in humid environments, for example. There's no reason apart from laziness. So one of the first things we often want to do is create this hierarchy so we know how to label the different parts of our system based on that preliminary configuration. And this makes it really easy to see how these components and parts interact. So let's go back to our smart lock with these different components and subsystems and what have you. You can see they're all labeled there. And this is a preliminary configuration. We haven't done any design yet. I don't care what anybody tells you, regardless of the fact we haven't done any design. You know that you will have these components or these subsystems or a list that's very similar to these components or subsystems in your final smart lock. And this is very, very powerful. And what we can do now is call blocks. You can see these blocks are called blocks because they look blocky. I've tried to find a rationale behind the word term block that's used in reliability a lot. But as near as I can tell, whenever you use a square to represent a component, they're just called blocks because they look blocky. And so we have our blocks here. You can see we have 17 different components. 17 components. 16 of them are different because we have 2 handles. And now we can arrange these blocks in a way that helps us see how they interact. So I've sort of smushed these blocks across the screen. And the reason I've done this is because I want to understand, like I said, how these components interact. So one thing I can do is draw lines between these blocks to represent a physical connection. And see, we've got a black line or grey line representing physical connection. Can anyone see a sneaky little block that has been added? Can anyone see it? Gold star gets awarded to the person who can identify the block that's been added to our diagram. The door, well done. So you can see in the bottom right-hand corner, we have the door. And this is not part of our system or part of our item, obviously, but it's very important to understand how a smart lock is going to connect with a door. Now, what's a very important reason to know or understand how or which component physically connects with another one? Any guesses? Interface analysis, yep. Fitment, yep. So make sure everything fits each other. What else? There's quite a few. Interfaces are the leading cause of failures. I'd agree with that. Some people suggest about 50% of failures occur at interfaces. So that's a very, very valid point. Energy, vibration, thermal expansion, sometimes chemical reactions. So that's a valid point, especially if an example might be something creates condensation on its surface, and that happens to be right and bolted to something which rusts easily. So it's really, vibration is also a very big one as well. So it's really important to understand what things are bolted to each other, especially the door, because that's how all of the vibrations in a way start. The door slams, the door being shut, everything else. And so it's important to include the door, but it's also important to note the door is not part of the item. So we're going to add this gray rectangle behind, which indicates where our item starts and where our item stops. Door interactions with humans, fantastic. And so this is one list of interactions or interfaces between, or one layer, let's call it that, of interactions or interfaces between the blocks, where each block represents a component. And then there's energy transfer, not just from vibration, which is from doors being slammed, but energy transfer, which is an integral part of our thing operating. And now you might see in the top left-hand corner, we have another block outside our system, which is for the building power supply. And that's building power supply supplies what we call the bridge. This is the bit which interacts with our smart lock over a local wireless area network, and that then interacts and interfaces with the internet-enabled local wireless area network that most people have in their houses. But that needs power to run. And so energy transfer, you can see, is very, very important. You can say energy transfer is between the electric motor and the gears, which drive the bolts. Of course, the handle can drive the bolt as well. And now we have the wire harness transferring energy as well, because that is all about electricity being transferred. Then we have another one, material exchange. Now, in this case, the material exchange is I include it in this conversation because it's a interface which is often included in textbooks and standards. You often see it in regards to things like manufacturing plants and the like. And I can just realize that poor old the shaft, 1.17, the shaft is not where it's supposed to be. It's 1.17 shaft is supposed to be between clutch 1.12 and 1.3. So, yep, send all your feedback to Fred about the inaccuracies and the amateurism of this webinar. I'll get onto it straight away. But the material exchanges are included as a rule in many of these diagrams, which show the interfaces, because they're very important. Manufacturing facilities, for example, where you're transferring, or maybe better yet, mineral processing facilities where ore is being transferred from one machine to another. Material exchange is very, very important to understand, because how material exchange from one machine to another is a source of many problems. So another one we're going to add is data exchange. Now, this one is not in a lot of textbooks and guidebooks, but there's no reason why you can't tailor this to whatever makes sense for your system. You can see you're exchanging data between the bridge, the PCB 1.5, and also the software, which interacts through both. And the software then interacts with the customer smartphone, the very, very top, another block. Then we have Bluetooth connection, very important to identify. So the customer smartphone will interact with a smart lock through a Bluetooth connection. And so we need to know that, because the smart lock is supposed to automatically unlock when a Bluetooth enabled smartphone is within, say, 5 or 10 meters. Then we have the Wi-Fi network in purple, and there we have another block on the outside. And you can start to see that we now have what we call a FMEA block diagram. Now, who said Who said that interfaces are the leading causes of failure? Samantha said, and I couldn't agree more. Actually, well, the number that I hear bandied around a lot, and I tend to repeat, is about 50%. But I could completely understand anyone who says, no, in their experience, interfaces are the leading causes of failure, because a lot of the times components do exactly what they're supposed to do. It's just how they're installed, how they're aligned, how they interact, how they interface, whether a PCB is bolted to an exhaust manifold. That's a big problem because PCBs don't like heat. Exhaust manifolds are nothing but heat in a way. And so it's not necessarily what these components are supposed to do. It's failure is often caused by one component functioning exactly how it's designed to function, ruining the day of another component next to it. And so the reason why we want to have these FMEA block diagrams is because it helps us see these interfaces and interactions. But we're still missing something. Can anyone see anything we're missing? There's an obvious one. What are we missing? Kevin, well done. People. We're missing the user who has the temerity to exert forces on the keypad and the handles. And so now we have a very important element of our system, or how our system interacts, and the poor old user that blocked in the bottom left-hand corner is perhaps the least predictable version of all those blocks outside. But now we know what parts of our system need to interact with humans, and that's a very big deal, because getting that interaction right is a huge ingredient when it comes to perceived quality, for example. And so the other thing that we might need to, we're talking about optical. Could you elaborate on optical? Optical is sort of an adjective to describe things that are seen, things that involve light. Okay, so the user is supposed to see the light emitted by the LED 1.15, and then talk about and then talk about how that LED is supposed to indicate a state. I could buy that. I wouldn't be able to. I could see that would be a very justifiable, what's called data exchange link between the LED and the user. What about would the user interact with the software? Now that's an interesting thing. The user would interact with the software perhaps through the customer smartphone. And so there's a case to be made that the software talks to the smartphone and the smartphone talks to the user. But by the same token, we all know the software sort of is directly building the interface you see on that smartphone. So therefore, you could make a case that the software interacts directly with the user itself. There's a strong case to be made for that as well. Happy with that. Yeah, I think Giovanni is talking to that point. Now, there's no right or wrong answer, and the reason why is because all we want to do is create a diagram which makes people think. And if that link between software and the user makes people think and identify another user interface, can't see any reason why you wouldn't include it, especially if you know how your team works and how your organization might struggle perhaps to identify human-machine interfaces. And there's one other thing I'll point out is that we might, for example, we know servers that process signals from the customer smartphone, they might be a very important part of how this thing works, but they might not be appropriate for them to be in this FMEA, because the FMEA we're going to do on a smartphone is very mechatronic or electromechanical, and you could make a strong case that the servers and the systems surrounding the servers are worthy of their own FMEA, and so for that reason they might be excluded and be included in another discussion. And coming back to what Samantha said, she said most failures occur around interfaces, and the number I hear is about 50%. Suffice to say, it's a big deal. If you want to drastically improve reliability of the system really easily, then getting on top of interfaces is one of the best ways you can do that. Carl writes, the RBD reliability block diagram is used to identify potential areas of poor reliability and where improvements can be made to lower the failure rates of equipment. This method can be used in both design and operational folks to identify poor reliability and provide targeted improvements. Any thoughts? I would not agree with your premise that RBDs will by themselves identify potential areas for poor reliability. I will agree with the premise if you say that RBDs in conjunction with extant component or subsystem reliability characteristics can help you work out which component or subsystem is ruining the day of system reliability, or it has the biggest impact on system reliability. And the same could be said of fault trees. And so that essentially helps you find the weakest link. However, that is a system reliability modeling thing, and then we do talk about that in other webinars. But I see where you're going. I think I agree with where you're heading, but I will say that RBDs will not of themselves tell you what you need to focus on. And the other thing about interfaces is that even though at least half, let's say that to align with what Samantha suggested, I usually are the first things we forget about. And having a FMEA block diagram like this can help you focus your FMEA group activity, which is a group activity, on these interfaces. So last couple of weeks I've been involved in FMEA courses and FMEA facilitation. And having this diagram or the equivalent of this diagram for the group analysis, the brainstorm of what might go wrong, was not just vital, it was necessary. We couldn't do it without it, because we need to focus on finding those interface issues. So to make sure we don't forget about understanding what those interface issues are, we need to be very, very clear about defining what our functions need to be. And so to do that, or to start with defining what failures are, we need to get on top of what our thing is supposed to do. So we know that failures are events where a system or item inherently ceases to perform a specified or required function. A function or functions are behaviors, processes, actions, or tasks that support a requirement. Now, a function is the language of the designer, the engineer, the manufacturer. We often talk in functions such as the Bluetooth must have 25 milliwatt power, or whatever it is. It must turn within 3 seconds. It must have this output torque of this, that, and the other. This is the language that engineers tend to use. Let's be clear. This is not what our customers often use, especially the customers of our smart. The functions are used to describe what our thing is supposed to do. And to be even more specific, we come up with specifications. We really describe that function to support what we call a requirement. Now, requirements are the language of our customer. Conditions or capabilities needed by a user or customer to achieve something. Now, I know there are systems engineers out there who say, hey, the terms that in textbook this and standard that, and guidebook this, they have different takes on what a specification is and a function is and a requirement is. Now, that's cool. So all I want you to understand is that in this conversation, requirements sit at the very top. They drive the specifications and functions. And once we define our functions, they help us identify failures. Requirements in this conversation are how customers or users would describe what they need to be able to do with your thing. So for a smart lock, they need to be able to walk through their front door. See, not one mention of the smart lock. They need to be able to walk through their front door of their house. But when it comes to the specifications and functions, that's the language of us, the engineers, the designers, the technicians, and we can sometimes get caught in this sort of very limited vocabulary where we don't talk about anything but functions and forget about what the customers are supposed to do. And once we have those specifications, which always include that function, what is the item intended to do, now we start defining what our system is or our item is. The idea is that we need to always link our thing back to a requirement, because a requirement is something that the customer is going to say that they could achieve, or in cases when your failure occurred, they could not achieve with regard to your item. So for example, for our smart lock, requirement number 1, to easily and automatically unlock when a customer or authorized user wishes to pass through a door. So this is from the perspective of the customer. It is not, for example, Bluetooth power of 2.5 milliwatts. That's the specification. And so we know there's lots of requirements for a smart lock in terms of how the customer would want to describe what they want to be able to do with said smart lock. We know that, for example, we want to keep unauthorized people out. We want to keep the bad guys out. It must be easy to install. That's a requirement. It needs to advise the customer or user of locked, unlocked status anywhere in the world. It allows the customer or user to lock it or unlock it from anywhere in the world. Give people specific access to my house for specific times. I want it to work with my existing house's IT infrastructure. I want it to not look bad or make my house look bad. And of course, there's plenty more than that. So this is all the language of the customer or user. And so once you have that, then you can start sinking your teeth into the specifications and functions. Now, when it comes to FMEA, FMEA group activities or group analysis, it's really important to get on top of this, making sure we get all those specifications and functions identified. This is a really easy trick where that amazing reliability engineer who appears a lot, who's always going to be brainstorming what essentially during a FMEA, she's asking us to brainstorm why this amazing thing will fail. When we say brainstorming, let's replace this thought bubble with thunderclouds brainstorming. Get it? It's a storm. So brainstorming. And brainstorming needs a language. And so to do that, and I need to owe this taxonomy to our friend Carl Carlson. I actually need to ask Carl Fred if it was something he came up with or something he heard. Anyway, I'm not going to claim any sort of credit for these different functions or different categories of functions. There are the basic functions, the obvious functions, the functions that allow you to call your item a noun. You can call something a bike, essentially, if it has the basic functions associated with the bike. Pedals that drive a wheel, two wheels, etc., etc., etc. Handlebars to allow the user to steer. If you have those basic functions, and quite a few, I've only just touched on some, then you can then come up with, you then allow it to call that thing a bike. If it's missing one of those basic functions, it can't be called a bicycle. So the obvious functions provide baseline performance. And sometimes we only ever focus on these, often wrongly think these are the most important functions. No, these are the functions which allow you to call the thing you create an angle grinder, a plasma cutter, a bicycle, a car. So the basic functions, we often get fixated on them as if they're the most important. They're not. Even though they are the most important from one perspective, in that they provide the central functionality that allows you to call your thing an angle grinder, a plasma cutter, or a bicycle, or a car. As a rule, we're actually pretty across them. We know how to do these things. The technology is well understood. It's how we make that technology reliable that becomes challenging. And so basic functions include something has to contain something. Something has to maintain a flow rate. Something needs to calculate numbers for control system. Something needs to secure one thing to another. Something needs to transform speed and torque. And of course, plenty of others. Now I can see I can see there's a couple of comments about functional specification and design verification and validation. That's cool. We'll come back to that one in a tick, because the next one we're going to talk about are functions that you cannot easily validate or verify sometimes. And we know that at least 50%, there you go, Samantha, of failures occurred in interfaces, a hell of a lot. So the reason why we're doing this is because during the FMEA, we want our facilitator to make sure that he or she is breaking up the brainstorming activity into conversations where we identify basic functions and conversations where we identify interface functions, including the fit functions. If we do this during a FMEA, it's the easiest way to improve reliability. If we forget about this during a FMEA, or actually any reliability activity, I should say, it's the easiest way to destroy reliability. So interface functions include, this thing needs to provide power to. Now, simply defining this function then requires us to have a specification. So what is the voltage of that power? how tidy does it, how clean does that power need to be? Is that if that power is dirty, if it has spikes, will it fry the thing it's connected to? All of a sudden, by simply identifying this function and then allowing us to think about the specification we need to come up with, that then forces us to think about how our power supply needs to provide power in a way which doesn't fry the PCB, or the PCB needs to be able to be designed in a way where it accepts dirty power or whatever it is that we believe it is harder to control. Another one is connects with, and that's very important because now we need to define the forces, the stresses, the vibration, everything else. Transmits torque too, as you can imagine, very important. Inputs data into, that's extremely important because a number of space probes and spacecraft which have impacted extraterrestrial surfaces at great rates because some components designed by the European Space Agency were expecting torque to be input in Newton meters, were instead being input in terms of foot pounds. So just getting the units of measurement right is very, very important. Does not exhaust heat onto, and plenty of others. Now, Samantha writes, is there a difference between contain and secure basic functions and interface functions? Now, I can see that is a very valid question. So in the real world during a FMEA, where you can see that, if, for example, secure, I think contains, you could argue if it's containing a fluid, the fluid is a material itself, is a material not part of the system. So contain might be seen as a very basic function, but secure might mean you're securing one component to another, which very much could be an interface function or a basic function from a certain perspective. And so when I run my FMEAs, I'm always open to it being categorized as either. And the reason I want to do that is because when I go back and review the brainstorm and I put a little b or little I or little a for additional functions, which we're about to talk into right now, it helps me see as a facilitator if I'm focusing on one form of functions. So before I depart from the interface functions, these interface functions, you cannot even contemplate coming up with or containing or being complete in their coverage if you don't have that FMEA block diagram. So the last group of functions are the additional functions. These are often seen as the least important functions, but because they include the form functions. Does it look good? Is it safe? Is it easy to use? Is it easy to maintain? Is it comfortable? And the reason why these are often seen as the least important is because often people will say these are the nice to haves, and they're absolutely not. For example, it's not nice for it to be safe. It's not nice enough, nice to have for it to be, as Giovanni points out, high quality. Is it easy to maintain? If it doesn't look good, people aren't going to buy it. If that bicycle is not comfortable, people are not going to buy it. And so while the basic functions are often the central impetus behind a product, an item, or a system, by the same token, they are also in our wheelhouse. We usually know how to calculate flow rates and torques and everything else to make things turn and the rest. However, it doesn't work like that in the real world, where the difference between success and failure is often the interface and the additional functions. If you don't think about the interface functions, it won't be reliable. If you don't think of the additional functions, then your product or item won't be considered good. Now, some people say, well, this item is going to be used in our manufacturing facility or in our processing plants, and so therefore these additional functions, they're still nice to have because, is it comfortable? Does it look good? That's just, we're not interested in that sort of stuff. Well, is it easy to maintain? Guarantee you're definitely interested in that stuff, because if your thing is very difficult to maintain, that is to change a bearing, which needs to be changed out quite regularly, you have to take the entire powertrain out of something, that's not good design. That's an additional function. Technically, your machine can still do what it's supposed to do when it's got that bearing replaced. But if it's 3-hour downtime for what should be a 5-minute replacement, that's an additional function which is going to cost your organization perhaps millions of dollars over the course of a year. So the additional functions are the bits that make your thing good. Do all fasteners require a single tool? Is it childproof? Does it have, is a function include the ability to have modular skin? So for our smart lock, is it easy to change the aesthetic look of each lock? So we can easily have one which is brushed steel versus polished nickel or whatever it is that people are desiring these days. What about interchangeable left and right hand grips for comfort? Does it comply with environmental regulations? Now, this is an additional function, but if you don't comply with, for example, European Union environmental regulations, which is very different to North American or Australian or New Zealand or now British regulations, then you just got a whole market segment you can't sell your thing to. And of course, there's plenty of others. And so the idea is that when it comes to brainstorming a FMEA, if you as a facilitator have these three functions in your mind when it comes to facilitation, as a rule, when people start brainstorming those functions, they will start dribbling out at a great rate of knots the basic functions. And there comes a time where you, the facilitator, says, okay, we've got 80 basic functions up here, can't see a single interface function or a single additional function. So let's start thinking about interface functions. And that then challenges the team or changes the team's focus to start coming up with those interface functions to help you make it reliable, and those additional functions to help make your product good. And the FMEA block diagram is brutally important, as you can imagine, for the middle thing. Those basic interface and additional functions, which become the language for brainstorming why things fail. And so in the guidebook, you'll have a little bit more information about how to make that work. In the guidebook, you'll also have a bit of discussion or an example of how to include these in your FMEA worksheet and how a FMEA should be looked at as well. So I'm going to call it quits right there, but I did promise we talked about specifications being critical in design, in defining the system prior to design verification and validation. That's cool. So as a rule, though, I'd want us to focus on designing. Verification and validation, often, of course, it's very, very, very important in terms of being able to comply with what we need to do to generate confidence that our thing fits the bill. But verification and validation don't make things reliable. They just measure it or observe it or test for it. So you can have the world's best verification and validation process, but if your design process is terrible, then all your verification and validation process will do is very accurately tell you how terrible your item is. If you have the world's best design process, but a terrible verification and validation process, then you're going to create very reliable, very robust things, which is really, really useful. Now, people will say, but you can't have one with the other, out the other. That's cool. But if you have a fantastic design process where you're thinking about interface functions and everything else, then verification and validation becomes very, very simple. And Giovanni wrote that functional analysis techniques need to be used, but is really hard. Now, I'd argue that depends on how it's sold. If you have a great facilitator who's able to control that conversation, you can really get on top of some very nuanced interactions between components and how things are supposed to do what they're supposed to do in order for you to identify those interface functions. Now, that FMEA block diagram itself is really, really, really helpful. Now, when I can facilitate a FMEA, we never, ever generate the FMEA block diagram as part of the FMEA activity. Why is that? We do it beforehand. If I'm the facilitator, I might sit down with a smaller group of people who may or may not include some of the participants in my FMEA activity and get the FMEA block diagram done. I'll review it. I'll ask other people to review it. I'll then share that FMEA block diagram with participants by email, for example, before the workshop commences. And yes, we'll put the FMEA block diagram up and give people last chances to identify any discrepancies or issues. But by that stage, we should have a pretty agreed upon FMEA block diagram. That said, I've never done a FMEA where we haven't identified one potential change to our FMEA block diagram in terms of interactions. And so it doesn't mean it's laminated forever. However, I do not want to generate a FMEA block diagram from scratch during FMEA activity itself. That is not the point of a group activity. We're trying to focus every minute we have on brainstorming. So on that note, are there any questions? Giovanni writes, can you specify the difference between durability and robustness? The answer is no, because there's about 75 different takes of what durability and robustness means. Durability, some people will tell you, is essentially the ability for it to last a long time, which then has reliability connotations. Robustness is often put forward as the ability for your thing to operate outside its use case, its specified operating conditions or environmental profiles. And the reality is there are two sides of the same coin. You can never predict with absolute certainty how your customers will use your item or device. An example I often use is the first generation mobile phones or cell phones, those big bricks, those big, very expensive bricks that were sold in the late 1990s, very clunky, very large mobile phones, and they worked, but they're extraordinarily expensive, and they were initially sold as luxury items, but it turned out that the market segment which sort of drove the profit-making capacity of the mobile phone industry, at least in the early days, were tradespeople, the plumbers, the electricians, because even though those phones were expensive, they were cheaper than having electricians and plumbers drive back to the main office to get the job card for the next job. So instead of having to do that, all they needed to do was get the mobile phone, ring the home office. The operations officer would say, okay, you need to go to this address of this house, and off you would go. And so lots of organizations who started manufacturing cell phones and mobile phones very quickly went out of business because they were focusing on the perfect or luxury customer, one who's not going to throw that or expect to have that mobile phone or cell phone rattle around in the toolbox. Those who are producing robust phones, they're the ones who survive, because those robust phones are the ones that are being which were popular amongst the tradespeople. Brian writes that durability can include items which are designed to wear out, but they achieve the desired life. So things like brake pads, for example, yes, they wear out and they'll eventually fail from one perspective, but if they took the requisite amount of kilometers or miles to before they failed, that's also cool as well. By the same token, brake pads are a great example of how it's difficult to understand how long brake pads should last in terms of distance, the most common usage metric for vehicles, because different people have different braking characteristics or braking tendencies. So if you have someone who's very heavy on the brakes and is driving the suburban roads, having to turn left or right every 100 yards or so, brakes are being used a lot compared to someone who does most of their driving on the freeway, the highway. A lot less braking occurs. And so, yeah, durability is often about how long something lasts. Robustness is about the ability for things to operate outside the nominal operating conditions. The reality is you don't often get durability without robustness. While Fred is trying to make that guidebook visible, shareable, any more questions or comments? I might even finish the conversation by going back to that FMEA block diagram, which was the impetus for today's conversation. Let me find it. So this one. Of course, it's missing a couple of things, but there we go. Very powerful visual tool. What's your opinion on software like analysis in the physics of failure? So I'm guessing you're talking about Giovanni. An example could be finite element analysis. Big fan. Sherlock. Yeah, so finite element analysis is great for understanding shocks through, or sorry, not shocks, stresses through materials. But you're talking about Sherlock, which is very useful for physics of failure when it comes to PCBs and vibration analysis and things like that. And I think Sherlock is quite useful. It's very useful, especially when you're trying to get those first prototypes. Let's just say you're going to design a PCB in a smart lock, and of course, when you're designing a PCB and a smart lock in a door which can slam shut, one of my concerns is vibration. So Sherlock might be very useful in designing the first PCB to try and understand how vibration is going to ruin the day of capacitors and resistors. I still might be motivated to use Sherlock to create those prototypes that then get tested or be getting subjected to halt testing. But I think Sherlock, finite element analysis, and other things are incredibly useful, only if you are very clear about where their boundaries stop being, or what they can't do for you. So I think those sorts of things can really help you get a long way in those first design iterations, those first prototypes. But then there's often going to be a need for subsequent things like halt, especially for vibration sensitive systems like the smart lock. There might be some scenarios where your device isn't going to be used in a very violent vibration centric operating scenario. For example, a desktop computer is not going to be moved around a hell of a lot. So you might be happy that things like Sherlock can satisfy your vibration concerns. So without saying there's a right or wrong answer, it's just, I think they're very useful as long as you know what they can and can't do. Thank you, Giovanni. Much appreciated. Any more questions before we call it quits for this week, for this month? No worries. So as you can see, I'm a big fan of FMEA block diagrams or anything that visualizes how things interact with another. So Samantha points out, most failures, or at least half failures, will occur at interfaces. So if you want to really easily improve reliability, get a FMEA block diagram up and running to work out how components interact, and then make sure you focus on working out how those components need to look after each other. Why can't we all just get along? Thank you for the feedback. Thanks, Kevin, Carmen, Carl, and David.